We'd like to solve algebraically to find the exact value of x. Since we've got 3 to the x minus 2 is equal to 10 to the 4 minus x, our x's are in the exponents here, and it would be nice if we could match the bases of these two sides. If this were a 9, that would be convenient because 9 is 3 squared, and then we can just look at the powers after that. But since there is no way that we're going to be able to write 3 to the power equals 10 to the power, we're going to have to use properties of logarithms in order to solve for x. So we've got a property that says the log base a of m is equal to the log base a of n, implies that m is equal to n. So we can go back and forth between these two forms. This is log form and exponential form, depending on what it looks like when it's done. And we can also choose what we want to use for the base. Now, this problem states that we want to find the exact values. So when we're done, we should expect logs in our answer. I prefer to use the natural log for these problems just because ln is shorter to write than log base whatever. Now, some convenient bases to use in this problem could be log base 3 because we have a base 3 here, or log base 10, the common log. So those are some other good options, but I'm just going to use the natural log. Now we're going to take the exponent property and rewrite x minus 2 times the ln of 3 is equal to 4 minus x times the ln of 10. Since we need the exact value, we can't just type this into our calculator and get decimal numbers. Those are not exact values. So to make this a little bit easier to work with, I'm going to call A the ln of 3, and I'm going to call B the ln of 10. That way I can solve my problem for x, and I don't have to keep around the ln of 10 and the ln of 3. I'm going to treat A and B as constants because that's what they are, because the ln of 3 is a number and the ln of 10 is a number. So we're treating those two as constants, and then we're just going to solve for x as usual. This is a linear equation, so we have ax minus 2a after distributing is 4b minus bx. Let's get all the x's to the left-hand side and all of the numbers and the constants to the right-hand side. Adding bx to both sides gives us ax plus bx. Adding 2a to both sides gives us 2a plus 4b on the right-hand side. Now, on the left-hand side, I can combine like terms since they both have common factors of x. Essentially what we're doing is we're factoring out the x, and we have a plus b, whatever number this is plus whatever number that is. And that is equal to 2a plus 4b. Now we can divide both sides by a plus b and solve for x. But what was a plus b? Well, a was the ln of 3 and b is the ln of 10. So we can write our final answer in exact form. 2 times the ln of 3 plus 4 times the ln of 10 over the ln of 3 plus the ln of 10. If we want, we could use some properties of logarithms to combine these to make it look a little bit nicer. So let's do that. Let's use the power factor property to rewrite the top as the ln of 3 squared plus the ln of 10 to the fourth. I'm not going to do anything with the bottom on this step. And on my next step, I'll use the addition multiplication property to write the ln of 3 squared times 10 to the fourth divided by the ln of 3 times 10. Now, note, the top is the ln of something and the bottom is the ln of something. We don't have any properties of combining those, so I want to leave my answer in this form. You cannot have the arguments of these two functions interacting with each other. That is, there is no canceling of a 10 in the denominator with a 10 in the numerator, because order of operations say you have to do this ln function before you can do any other operations. So that's my answer in exact form. I guess if you don't like those exponents, you can write 3 squared is 9, 10 to the fourth is 1 with some zeros here. So there you have 9 times 10 to the fourth over the ln of 30. If it says find a decimal representation of that, at this point we can type it into our calculator, but that is the end of that problem.